All right, in this section, we're going to look at a couple of tests. It's really one test and then a special case of that test. But it's important to note that these tests just apply to series that have positive terms. And the basic kind of backbone test of this section is the integral test. So it goes like this. Say we have a function that is positive, continuous, and decreasing for all values of x that are at least as big as 1. And we form a sequence, some terms, that are equal to the function terms evaluated at the integer values. Basically just say if you take that function and evaluate it only at the integers, at the positive integers, then you form that sequence. And then make a series out of those terms. Then that series and this improper integral from 1 to infinity, they either both converge or they both diverge. So essentially it's a way of saying, look, I've got this series, the terms are all positive, and I can look at the continuous function, like if I just extend the way that series is defined to all the positive real numbers. If I can figure out what that improper integral does, then I know my series does the same thing. So here's an example. Let's just sort of see how this works. We'll note that the terms of this series are all positive, right? Because n starts at 1, and n over n squared plus 1 is always going to be positive for those values. If I'm going to use the integral test to examine this series, the first thing I have to do is define my continuous function. So I just take, I define my continuous function in this way. I take the way that those terms are defined, n over n squared plus 1, and I just say, you know what, I'm going to change all those to x's. X over x squared plus 1, and I'm going to say this is a function, a continuous function. I'm not restricting it just to the integers. I'm going to look at it on all positive reals where x is at least as big as 1. Then I have to make sure that the integral test applies. So that's up here in the beginning. We have to make sure that the function is positive, continuous, and decreasing. So certainly f of x is positive as long as x is at least as big as 1. So we could check that off. Is it continuous? And for this question, we mostly are going to look for, are we in danger of dividing by 0, or are there any domain restrictions? And x over x squared plus 1 is definitely continuous. It's continuous for all values of x, but definitely continuous for the values of x that are at least as big as 1. So this gets a yes, and just going to write a quick note that we're going to look for rational functions like this, we look for division by 0, right? We see if we're at risk of doing that. And then the last criteria is that we have to show that it's decreasing. If we're able to answer yes to this third one, right, if we're able to answer affirmatively for all three, then we'll go ahead and look at the integral, that improper integral. So there's a couple different ways to look at this. As x increases, both the numerator and denominator increase. So that could make it hard to determine that it actually is decreasing for all values of x. But one way that we have to examine a function for, checking to see if it's increasing or decreasing is just look at the derivative and see if the derivative is negative. So f prime of x, we could use the quotient rule on that. So g f prime, so it would be x squared plus 1 times 1 minus f, which is x, times g prime, which is 2x, all over g squared. Gonna simplify the numerator. So we have x squared plus 1 minus 2x squared. That's 1 minus x squared. So here's our derivative. Now the denominator is always positive because we're squaring some stuff. The numerator is definitely negative as long as x is at least as big as 1. Or it's less than or equal to 0 as long as x is greater than or equal to 1. So that means we can answer yes to this. Now that we've answered yes to all 3 of these questions, that means that it'll be worth our while to set up the improper integral and see what happens. So I'm looking at the improper integral from 1 to infinity of our function x over x squared plus 1. This is, of course, a limit as b approaches infinity of the integral from 1 to b of x over x squared plus 1. Now, a quick examination of this integral. I think this looks like it fits the log rule because the top is just about almost the derivative of the bottom. I just need to add in a factor of 2. The derivative of x squared plus 1 is 2x, so I'm going to throw that in there. Put the factor of 1/2 on the outside. So now this integral is ln of absolute x squared plus 1. Of course, x squared plus 1 is always positive. So I'm gonna not bother with the absolute value signs. And let's see what we got here. Ln of b squared plus 1 minus ln of 2, when we plug in 1, that ends up being 2. And now we just want to evaluate this limit. Now, the ln function, ln of 2 is constant, so that's obviously as b approaches infinity, ln 2 just stays put. The question is, what happens to ln of b squared plus 1? So, the argument here, that's approaching infinity. So what happens to the log function as the argument inside blows up? We could examine that by taking a quick look at the graph. And really I'm just going to look at ln x, right? I mean, the big question is, what happens to ln as the stuff inside gets huge? So I can determine this whether I put in ln of x squared plus 1 or ln of x. So the ln function and I'm going to say go from, our x's are getting huge, so I'm not going to go any smaller than 0. And I guess that looks like a decent window. Whoops. So there's that function. Now it's not like, it doesn't look like it's blowing up, right? It's increasing for sure. It doesn't look like it's increasing very fast, but let's let x go out for a longer period. Let's say I let x go out to 100. That just keeps getting bigger and bigger. I could let x go out to 10,000. And it just keeps increasing. So the observation here is that the ln function just keeps increasing. The log function is always increasing. That means that as the argument gets huge, the log function also approaches infinity. It doesn't do it very fast, but who cares? So this limit is infinite. So what we've determined here, the improper integral diverges to infinity, and since the integral test applies, that means that the series diverges. It's really important when you're done applying, when you're done evaluating the improper integral that's a part of the integral test, that you actually say, do the extra step. It's actually not an extra step, it's needed. They actually make your conclusion about the series. We can't stop at saying what the integral does. We have to draw a conclusion about the series. All right, this next series we're going to look at is 1 over n squared plus 1, so similar to the last one. Only our numerator is 1 instead of n. So again, we're going to start, we have to start this. If we're going to use the integral test, we have to start by picking our function. And that's usually the easy part, right? Just change those n's to x's and treat it like a regular, a regular function that we're used to working with. So we're going to let f of x equal 1 over x squared plus 1. This is positive always. It is continuous because we're not in any danger of dividing by 0. X squared plus 1 is not going to be equal to 0 ever. So there's no issues, there's no domain problems. It is defined for all real numbers, in fact. Certainly for all real numbers greater than or equal to 1. And then, is it decreasing? Now, we could check like we did the last one and find the derivative and show that it's going to be negative for all for all values of x, or at least 1, and that'll work. And it's actually not that hard. You could actually check that out. But that's not our only option. We can tell it's decreasing because as a fraction, right, the numerator is fixed. And the denominator is increasing as x squared, as x increases, x squared plus 1 certainly increases. So if you take a fixed numerator and its denominator is increasing, that means that the fraction has to be getting smaller, right, as x increases. So that we could also just sort of make a simple argument in that way. That argument was harder to make in the last example. Because both the numerator and denominator were increasing. So we kind of needed to rely on the derivative then. So anyway, we've been able to answer yes to all 3 of these. That means it is worth our while. We're going to bother with setting up the improper integral. So we're going to integrate from 1 to infinity the function 1 over x squared plus 1 dx. And of course, the improper integral, that's a limit as b approaches infinity. From 1 to b, 1 over x squared plus 1. This is a form that we know. Maybe we haven't used it in a little while, but it does come up from time to time, and I'm sure it came up at least a few times when you were doing the exercises in partial fractions. It's one of the common forms that results from that process. But this is an arctan form. So the integral of 1 over x squared plus 1. That is the arctan of x from 1 to b. So this is the limit as b approaches infinity of arctan b minus arctan 1. Now, arctan of 1, that's a constant. In fact, arctan of 1 is pi over 4, right? Arctan of 1 is what's the angle that we plug into tangent to spit out a value of 1. So we know that this here is equal to pi over 4. And boy, let me write that a little bit better. Okay. Now the question is, what happens to the arctan function as the argument b blows up? So as b gets huge, arctan of b does actually approach a value. And when we want to know, I'm going to kind of use some of this margin space. If we're interested in what is the limit as b approaches infinity of arctan b, what we're trying to do, since the argument of arctan is getting huge, that means we want to know, where does the tangent function blow up? Where does the tangent function blow up? So to answer this, certainly you could look at a graph on your calculator. Just make sure your calculator's in radian mode, and you can kind of suss it out that way. But I think the easier way and a more sort of meaningful and kind of straightforward way is to think about what the tangent function is. One way we define the tangent function, tan theta, is sine over cosine, sine theta over cosine theta. And if we want to know where the tangent function blows up, right? So what makes that tangent function get huge? So there's two ways that a fraction can get huge, right? It either happens because the numerator gets huge while the denominator maybe is staying put or not moving very much. And we know that that's not happening. We know that the sine function does not get huge. The sine function is bounded. Sine theta is always between -1 and 1. So the other way that a fraction is going to blow up is if the denominator approaches 0. So this gets huge when cosine theta approaches 0. And the cosine function approaches 0. That happens, let's see, think about the unit circle here. Cosine is the x-coordinate, so the x-coordinate gets 0 when it approaches the top of the circle. That's at pi over 2 radians. So that's when theta is approaching pi over 2. Alright, so now we know that tan theta blows up at pi over 2. Let's bring that down here. We can now evaluate this limit. So as b approaches infinity, arctan of b is approaching pi over 2. So this is pi over 2 minus pi over 4, which is equal to pi over 4. So now we've evaluated the improper integral. Now we have to finish the problem by drawing a conclusion about the series. Now this is a really important part. I mentioned that before. We can't forget to say what our series does. But when we are able to determine that our integral converges, here's what that allows us to say. That allows us to say that this series 1 over n squared plus 1 converges. And it allows us to say nothing more. We don't know what it converges to. We know that the integral converges to pi over 4. But the integral and the series are not exactly the same thing. You know, the integral is this magic adding machine that adds infinitely many things, but it grabs so much more. The improper integral actually gets more stuff than the improper integral does. The improper integral grabs more stuff than our series does. So we could say what pi over 4, we could say that the integral converges to pi over 4. That just allows us to conclude that this series converges. We don't know what the sum is. All right, let's try another one. This series, the terms are given by 1 over n ln n, and note here that the terms start when n is equal to 2. That means when we look at the, when we define the function, we only need to define that function where x is at least as big as 2. So we're going to let f of x equal 1 over x ln x. Now, when x is at least as big as 2, f of x is definitely positive and it is continuous. Both x and ln x are positive for values at least as big as 2. So that means that the whole function's got to be And it's continuous because there's no issues with dividing by 0. Dividing by 0 would only happen if x is 0 or if x is 1. That's what makes ln x equal to 0. And we only have to look at it when x is at least as big as 2. So we know it's positive and continuous. Now we're just going to check, is it decreasing? And again, you can check the derivative and show that it's going to be negative for show it'll be negative where x is at least as big as 2. And that isn't too hard, but also we know that as x increases, both x and ln x are increasing. So we can make the similar argument as we did the last time. We could say that's got a constant numerator and an increasing denominator. And that means that f of x is decreasing. Where x is at least as big as 2. So either of those will work. If you want to make this sort of simpler argument that doesn't require the derivative, just make sure that your argument is sound, right? That's not really an argument that I could have made for this function, because both the top and the bottom are increasing there. But it works on this one and the last one. So that means, it's positive, continuous, decreasing. So that means that the integral test applies, and we're going to look at the improper integral. Now we're not going to integrate from 1 to infinity. We're going to integrate from 2 to infinity. Oops. Because that's lower limit's got to match up with where our series starts. Now, maybe we need to stop and think a little bit for, like what comes to mind as far as how do we integrate this. A simple U substitution will work. Maybe you want to pause the video first and see if you can't figure it out before I show you what I've got in mind. But we're gonna set up this limit as b approaches infinity, and we're going to integrate from 2 to b, and I'm going to rewrite this function as 1 over x divided by ln x. Now this integral fits the ln rule because 1 over x is the derivative of ln x, so we can integrate that. It'll be ln of the denominator, so it actually looks like ln of ln x. And now we'll plug in our limits of integration. Now ln of ln 2, that's a constant. And as b approaches infinity, we've already observed that ln of b is going to approach infinity. And since ln of b is approaching infinity, then ln of ln b also approaches infinity. It approaches infinity very slowly. I mean, if you throw ln of ln x into the calculator, it will make a slow crawl, but it will always be increasing, and there will be no upper limit to the values that it can attain. So it does in fact approach infinity, even though it does so slowly. So this improper integral diverges, and that means that our series diverges. Okay. So now we're going to look at a special kind of series, and this is the other test, convergence test that we were alluding to at the very beginning of this section. It's really just an application of the integral series. It's a generalization of the integral series for a special kind of series. A generalization of the integral test for a special kind of series. So a series that looks like this, whose terms are 1 over n to the p, that's called a p-series. Note that n is the thing that is changing. It starts at 1 and goes to infinity. P is some fixed number. So the terms are like 1 over 1 to the p over 1 over 2 to the p plus 1 over 3 to the p and on forever. That's called a p-series, where p is a positive constant. If p is equal to 1, the series that you get looks like this, and this is called the harmonic series. And Theorem 20 just gives us a nice, neat test for how to tell when a p-series converges or not. A p-series will converge if p is strictly greater than 1, and the p-series will diverge if it's between 0 and 1. The theorem is easily proved just by applying the integral test. And just, what does your integral look like, for different values of p. So in example 522, we want to determine the convergence or divergence of the series whose terms are 1 over n squared. So we just have to recognize this as being a p-series. So this is a p-series with the value of p equal to 2, and just say, look, that's bigger than 1. And that means that the series converges. And that's all we got to do. So it's not that the p-series, it's not that we're always allowed to skip the integral test. If our series is of this special form, if it really is just this simple, 1 over n squared, not 1 over 3n squared, not 1 over n squared plus 2, right? Just 1 over n squared, then we could say, oh, that's a p-series, and I don't need to do anything more than observe that the value of p is bigger than 1, and say that it converges. And then just to finish out this section with a little bonus fact, an interesting fact. Look, for a lot of the series that we look at, the best we'll be able to do is determine whether it converges or diverges, and very rarely will we be able to say, oh, we know it converges to this sum, right? We could do that for telescoping series. We could do that for geometric series. But for most series, we're not going to be able to say what it converges to, just whether or not it converges. For this series, an interesting fact, the series whose terms are given by 1 over n squared, and starting at 1 and going to infinity, is equal to pi squared over 6.